I'm Masanori from the University of Tokyo. So today's my presentation title is Analysis of Demand Response Scenario by Industrial Consumer using the Artificial Electrical Power Market Simulation. So, first of all, I'll explain about our motivation for this study. The first one is carbon neutrality in electricity, and it is because global warming or climate changes are very important matter all over the world. So for addressing these problems, renewable energy is gaining popularity. For example, RE100 means renewable energy 100%, and many companies try to achieve RE100. Especially in this study, we focus on the factories, especially in Japan, and there is many ways to reduce CO2 emissions. First one is on-site generation on the factories. For example, setting the many solar panels on the cells of factories. And another way is PPA. PPA is Power Purchase Agreement for Renewable Energy. It is a kind of contract with power generation company, especially generating the renewable energies. And then there is other alternative way to reduce CO2. And the first one is renewable energy certificate, and other way is energy conservation or big part of the electricity usage. So, however, moreover, recently ESG investment, environment, social, and governance investment is also popular in the financial market. So, ESG investment also supports these approaches for the company to enhance their values. However, there is a very, very big problem here. It is renewable energy is very, very unstable. So this slide explains about another motivation of this study and the regulation of the electric power market. It is introduced for employing the kind of market competition mechanism to the price decision of the electricity power market. It aims to make electricity price lower or enhance causing a lot of innovation for the generating electricity or some kind of others. So also in here, Japanese electric power market was also deregulated in 2005. However, the regulation has also problems and challenges. First example is the price fluctuation. Usually in Japan, the price of electricity is usually 10 or 20 yen kilowatt per hour. However, in the last year, it goes up to 250 yen. And on the other hand, in the daytime on a sunny day, it goes down to the 0.1 yen. Price fluctuation is very, very significant. On the other, moreover, price movement are very complicated because the market mechanism makes the prediction more difficult because all participants have effect on the price. And the electricity is very hard to store. So because of those problems, electricity grid easily become unstable. For addressing those two big problems, demand response is a very, very promising approach, and we call demand response DL. And DL is a way to change the demand pattern to satisfy the demand supply balance. For example, in this video, here demand is overnumbered to the supply, total supply. So by using the DL, demand satisfies under the total supply. This is a very promising solution for instability of supply. Moreover, DL has I think DL has three benefits for also demanders. First one is, as I mentioned before, it gives stability to the power grid. And second one is CO2 reduction is possible. It is because usually high demanded period, the electricity is supported by the mainly peak load generation. Peak load generation is mainly uses thermal power generation, which causes a lot of CO2 emission. On the other hand, at night, many percentage of the generation is supported by the base load, including the, for example, nuclear energy or some kind of other, which is not emitted a lot of, not emitted a lot of CO2. So it helps CO2 reduction. Moreover, third benefit is the cost reduction. Because the high demanded field has a very high price, so cutting the demand on the peak load, it could also enable cost reduction. However, the DR is not widely used. It is because the effectiveness of DR is still unknown, and what strategy of DR is good is still unknown. So for addressing those problems, we perform this study. The purpose of this study is reviewing the effect of demand response by comparing multiple DR scenario for factory. And main target is the Japan electric power exchange market called JPX, and one factory of Japan electric industry company. And the approach is artificial electric power market. This is a kind of multi-agent simulation. So evaluation is a CO2 emission reduction and cost reductions. So we through this study we compare the how effectively DR can reduce the CO2 emission or cost reduction. So here is the outline of our simulation model. As I mentioned earlier, we employ the multi-agent simulation imitating the electrical power market. The benefit of employing the multi-agent simulation is we can consider the complex interaction between each participant and the market. So in this simulation, we employ one electrical power market and three types of agents. I explain about this detail in the later slide. So first, this is an explanation for the market. As a market in simulation, we imitating the supermarket in JPX. This market is divided demand for tomorrow into the 48 slot for each 30 minutes, and this market employing the pricing price batch auction mechanism illustrated in this slide. And this is the first type of agent. And this agent is the only agent to supply the electricity to the market, and we call generator agent. We employ the 300 agent, generator agent, and this agent employing the merit order to fitting the sell orders. Merit order is kind of the lowest marginal cost order. According to the order, this type of agent making their selling order to the market. As a generation method, we employ the two types of method. One is the base load method. Base load method is hydroelectric power generation and nuclear power generation. On the other hand, as a peak load generation, we employ the thermal power generation. And then using those generation cost, the merit order is built, and according to the merit order, they make a sell order to the market. And for the generation volume, we distributed the actual share calculated from the actual data to each agent are random, and selling price is decided using those three factors. First one is the best factor representing the actual generation cost. And church factor is recent price trending, and noise factor is also employed in those three factors. The weight for those factors differ among the agents, and this difference causes different price weighting and make a gradual supply curve. And as I mentioned earlier, we employ the two types of consumer agent. First one is this stylized consumer agent. We employ the 300 agent for this type. This type of agent is a kind of noise trader. It means representing other agents than the factory agent. So this type of agent is a very environmental agent. This agent is based on the actual usage and makes thereby orders. Demand quantity is decided based on actual data, and here actual demand data are distributed to the 300 agents are random, and they decided their demand volume. And price for buy order is also calculated based on the three factor. Here, three factor using here is a fundamental factor and trend factor and noise factor. Also here, the weight for each factor are decided randomly, and those weights are according to the exponential distribution. So the last type of agent is other type of consumer agent. We employ the one factory agent. This is a very targeted agent in this study. It is very important agent in this study. So we use the actual factory data, demand data. We extracted the stylized demand pattern of the demand pattern from the actual data. For extracting this pattern, we employed the PCR analysis, and we got the two significant principles. And the first significant principle is can be explained as the base demand for production, and the second factor was the seasonal factor, mainly air conditioner usage, and third factor is not explained those two significant principles. According to this analysis, we built a demand model for simulation, factory agent simulation. So demand volume are calculated from this equation, and this equation combining those three factors, which is explained from the PCR analysis. I mean the base demand, seasonal factor, and noise factor. So demand volume is decided based on the this equation, but the bidding price is assumed to be enough high price for execution. It is very strong assumption, but it is reasonable in this study because the factory agent always have to procure enough volume of electricity. So only this agent can activate the DR scenario. So in the following slide, I explain about the DR scenarios. So this is the concept of DR for our factory agent, and we have two criteria for making the DR scenario. First criteria is a peak cut or peak shift. It means peak cut is only cutting the peak demand, but the peak shift means that shifted the peak demand to the other time period. And other criteria is the selection of time period, because the time period selection is very important for efficient DR. So we also focus on this axis. So according to those figures, first figure representing the price movement, and second one shows the emission movement, and blue line means summer, and the orange line means the winter. And according to those analysis, we decided the selection of time period and make some audit. So here is all of the DR scenario we employed employed in this study, and we made 10 patterns of scenarios, memory 3 hours DRs, and 8 of 10 are systematically generated based on the previous criteria. Peak cut or peak shift 2 patterns times 4 patterns representing the how to select the DR period. First one is a fixed period, and other one is a price-based or shields-based or demand-based selection. I mean the DR period is selected based on the one of those indices. So according to those criteria, we made 8 pattern of the DR scenario, and the 2 other scenarios made in other perspective. And the first one is AC shift. AC shift means change the strength of air conditioner. It is a kind of shift, and the last scenario is a work time shift. Work time shift means move the working hour ahead to the morning, and so there is a pattern of scenarios. So in experiment, we also change the rate of DR. For example, 5% of total demand is shifted to the other time, or 10%, or 15%, or 20%, or like that. And we made the 4 levels of strength of DR. So here is the experiment and evaluation. The other experiment, we run the 100 twice of 1 year simulation for each DR scenario and each DR strength level, and evaluation performed according to those equations. And in this equation, the first means the rate. We calculate the rate of reduced or shifted demand and the rate of reduced cost, or the rate of reduced CO2 emission. And then using those rates, we calculate the cost cut efficiency evaluation and CO2 reduction efficiency evaluation. So in the following some slides, we explain the detail of the result, but it is very hard to understand even for me. So I skipped those slides, and this is a very, very simple and easy to understand result. This graph shows that the evaluation for the cost cut at once, and according in this figure, the horizontal axis means how well efficiently we cut the cost, and each bar means blue bar means summer, and the orange bar means winter. And according to this result, work time shift in summer shows a very, very good performance, and on the other hand, in winter, price-based flexible safety shows a good performance in cost cut. On the other hand, here is the CO2 reduction evaluation result. In summer, work time shift is a very good performance, and on the other hand, in winter, CO2-based or demand-based flexible shift shows a very good performance in terms of CO2 reduction. So here is the discussion on future work. In this study, we successfully evaluate some DR scenario in terms of cost cut efficiency and CO2 reduction efficiency. So according to our result, work time shift scenario in summer is the best performing scenario, very, very good performance. On the other hand, in winter, index-based peak shift works well. Those suggestions are very, very useful for planning DR for actual factories. As a future work, we consider the extension to this scenario to the case of introducing photovoltaic power generation or fuel cell or battery. And here is the conclusion. In this study, we built a multi-agent simulation for the electrical power market and analyzed 3 4 DR scenarios. And we also tested some DR scenarios and evaluated the cost cut and CO2 reduction efficiency. We found that the work time shift in summer, big shift in winter shows a very good the best performances. And multi-agent simulation were very, very beneficial for analyzing unknown social phenomena such as the complex effect of DR showing in this study. Other future work, as I mentioned in the last slide, more extension concerning other renewable energy for achieving the carbon neutrality is another possible work. This is the end of my presentation. Thank you for listening. And if you have any question, please let me know. Thank you.
Thank you for the presentation. So let's move on for questions and comment. If you have a question for the audience in the room, please just ask. Or here in the Zoom, if you are in the Zoom, please just raise up your hand and I will follow you. Okay, it seems to be a little bit quiet.
Okay.
Someone asking there?
Yeah.
Thank you for a nice presentation. It was very interesting. It might be out of your scope, but I think there is some topic by the climate change. What do you think about?
Sorry.
About the climate change?
Climate. Yeah. You mean this work or contributed to the discussion of the climate change or?
The climate change. So if today's also some power or something.
Oh, you mean the
impact from the climate change or the temperature?
Okay. So it is a very important point, but I think in this study currently we cannot consider the kind of climate change in the long span. But I think this work can be applied the case the climate is considerably changed from now. So because this study employs the kind of simulation, and simulation can consider any situation. This is the strongest of the simulation. So I think this study can also apply to those cases, I think, but in this study, currently, no consideration.
Thank you.
Thank you so much.
Thank you. Any other question? Okay, we have someone raise up hand, Professor Isashi Hayashi, please.
Yes, thank you for your interesting presentation. I think your conclusion that work time shift is effective. That conclusion is very interesting. But at the same time, this kind of research on time on demand responses or energy markets are very that kind of research is done for the past decades, and if you know some other researches on similar topics, can you explain that kind of similar research? For example, or what kind of demand response is effective, or CO2 reduction, or what kind of CO2 reduction policy is effective? That if you know or other researches which indicate that that kind of policy, which kind of policy is effective, if you know that kind of policy, could you explain that? I mean the related research.
Yeah. So it is a very important but difficult question because I think okay. So in terms of DL research for DL, there is many DL researches, but they mainly focus on the stability of the electricity grid. So we mainly focus on the cost efficiency or CO2 reduction efficiency. So this is a very different point from the other researches. But we are also those other research is also important because the DR is still under developing because no one knows which kind of DR is good, or no one knows everyone employing the situation, everyone employing the DR scenario. What's happening is still unknown. So the more DR analysis is important for important, I think.
Okay, thank you very much. So even now, in your opinion, which kind of DR policy is good is unknown still.
Yeah, still unknown because especially in this study, we only focus on the one factory of company. So this company is considering the employee DR for many purposes, but in terms of cost and CO2 reduction, it is very important to how the DR works is still unknown because how DR is still unknown. So this is mainly focused on the consumer in the industrial area. So in the study, we cannot consider any kind of policy from of the government. So this is another future work, I think.
Okay, thank you very much.
Thank you.
Thank you so much.
Any other question? Okay, so we are running with the time. Okay, let me have this question here. I think that is a very probably basic question. So what was the, for multi-agent simulation, Professor, did you use a specific tool for this simulation, let's say a programming language or a particular tool for this simulation, which can you tell us a little bit about that?
Yeah. So basically, we use Java platform, and with the platform is called the PlanJ. But this simulator is mainly made for the financial market. So we extended this simulator to the for the electricity power market.
Thank you.
Thank you.
Any other question from the room here in the Zoom? Okay, so lastly, would you just go back to page 9, I think?
9.
Yes.
This?
Okay. Yeah, a very basic question. I was following the mathematical expression here. What's the meaning of WFJ, for example? The denominator.
Which part?
Weight, WFs, the W.
Oh, okay, wait, the meaning. Okay. Okay, the meaning is how the agent considers which of the factor is important, because each factor, F or C or N, representing the fundamental or trend and noise factor, which is a very simple one, but introducing the weight for those factors, we can introducing the kind of homogeneous to the agent.
Okay. Once again, thank you for the presentation and even for the explaining the questions you received. Thank you for your research. We wish you all the best.
So much.